Hi there. We're going to round out the exponential and logarithmic models. We've already looked at exponential growth and decay models, which are the typical exponential growth or exponential decay shape, where the graph only ever increases or only ever decreases. These functions are one-to-one, and we also say that they are monotonically increasing or monotonically decreasing. Monotonically just means always. What we did was to find the equation and represent the set of data or the information provided from a real-world scenario. We did that by making a table of values, we did that by plotting the graph, and we did that by using the points or the values from the table to solve for the unknown parameters a, b, and c. Once we had the algebraic model, or the function, we were then able to use it to predict what the value of x might be if we knew y, or vice versa, what the value for y might be given x. There are three more models that we will look at. One is a logarithmic type, and the other two involve exponential functions. But you can see that the exponential graphs are not the typical increasing or decreasing exponential growth or decay. The logistic model is still an increasing function, but the rate of increase changes at some point of inflection. And the Gaussian model is what we call this bell curve or standard distribution curve, and this is typically used to represent populations. We're going to take a look at this one next. Gaussian models are of this form, and they have, for the equation, they have this maximum point which occurs for the coordinates b and a. So x is b and y is a. X typically represents the value of some population, so it might be some characteristic of a population, and by characteristic I mean the height of a population, maybe of all 6th grade students or all basketball players or even just all people. And so this characteristic of a population is the input variable, and the output variable, the y-coordinate, is some kind of distribution or percentage of people. And so when we're looking at this value here, this a-coordinate, depending on how we've scaled or reflected this y-coordinate, this might be a percentage, so we might expect it to be less than 100%. Typically what we're finding then is that the average or the mean of the population is the x-coordinate of the maximum point. So let's take a look at an example. In this question we have not quite an exponential curve, we call it a Gaussian curve or a Gaussian model or a normal distribution. And here we have x representing the number of time measured in hours per week that a student utilizes a math tutoring center, and y then is going to represent kind of the distribution or maybe the percentage of the population that we are sampling. So here the density of probability, you can think of that as a percentage. So we want to graph this function using the graphing utility, and then we want to estimate the average number of hours per week, which is really the average value for x that a student is going to use this tutoring center. So let's take a look at our graphing program. And here we've got the function, and we've got a restricted domain from 4 till 7. And we notice that this graph has a maximum point at 5.4, 0.7979. So about 80% of the students, that's kind of the population distribution there. And I just want to point out that this vertical line, x equal to 5.4, intersects with the maximum point. And we can see that that cuts the graph into two equal halves, and that is the number of hours per week, which is the average or the mean of the population. So now that we've got our distribution, we're just going to plot the graph, label the ordered pair for the maximum point, and use that to interpret the answer. Now, in a statistics class, we would be understanding the different parameters and the different values of the equation in a little bit more detail, and in fact maybe even coming up with this equation. But for now we just wanted to see another example of an exponential function, even if we're not going to do the same depth of analysis that we did for the y equals a times b to the x plus c exponential growth or decay. We just wanted to see another example of it. And so estimating the average number of hours per week, x is 5.4 hours per week for the average number of hours that a student uses the tutoring center. There's another type of exponential function that we want to look at, but it's not the characteristic exponential growth or decay. It's called the logistic model. The logistic model has an equation that looks like this, and we see that the e to the x, or the e to the something x, or the base to the x, is in the denominator. And we also have a graph that at first looks like the exponential growth model, but then we have an almost upside down concavity of the exponential growth. Over time, if x is time, the heights on the graph continue to increase. So the graph is an increasing graph. In other words, the y values increase as the x values increase. But what's happening is that there's a point here before and after which that the rate of growth changes. So we have an increasing rate of growth up until this point, which we call a point of inflection, and then a decreasing rate of growth. The rate of growth is still positive, so that the population or the y values are still increasing, but the rate at which it changes goes from being an increasing rate of growth to a decreasing rate of growth. This is really a useful model when we have a population that doesn't continue to increase exponentially. And so we're going to take a look at modeling population. In number 9, we're given the population of Florida from the year 1900 to the year 2000, measured in millions of people. Now, we don't expect that as time goes on, that the population of people just continues to grow exponentially. The ecosystem can't sustain that, and so there would be some leveling off of the population. So we would expect to use something different from an exponential growth model. We're going to create a scatter plot in Desmos for the population of Florida versus time, and we are going to take time equal to 0 to correspond to the year 1900. So we're not going to take the year x equal to 1900. We're going to make an x value correspond to 0 and then 10, 20, and so on for the years from 1900 to 2000. So let's go to Desmos. And it's really quite a nice way to make a table of values. I've already put the data in here, but to come up with the data, to come up with the table, you go to this plus sign, and then you just add the table. Now you'll notice that my first table of values had x1 and y1, but this table has x2 and y2. And so then you just start to put in the table coordinates for the x and the y, the data, and I like to go down the column for x and then down the column for y. So you can do that. And then once you have the table inserted, we can take a look at the scatter plot. Now we want to make sure to customize the window, which we can do using this wrench icon to come up with the graph settings. We can see that there are x-axis and y-axis values. I want my x-axis to go a little bit smaller than the smallest x and a little bit larger than the largest x. So -10 to 110 would be good. And I don't want to step by 1 because that's too many tick marks or too many grid marks. And I'm going to step by 10, which the graph is already seeming to do. Now for the y coordinates, I want to go a little bit lower than the smallest y value and a little bit higher than the largest y value. And I also like to go into the negatives so I can see a bit of an overhang before and after the origin. So I'm going to go from, say, -5 to 20. And here I will step by 1 because that does seem not to be too many tick marks along the vertical axis. So here I have my scatter plot, and it certainly does seem to be, well, it's an increasing graph. And what we're going to do is come up with a model or an equation, not by hand, but using a regression or curve of best fit. To do this, we're going to type into the next box, and I'm simply typing y1. When I do that, it automatically comes as a subscript, this 1. And it's referring back to the list of y1 data values here. The next part is not to use an equal sign, but to use this kind of curvy line, which we call a tilde. And we are going to, this is kind of the regression operation. It cues the program that we're making a regression equation. So it's going to fit the data with the best possible equation. Now we need to tell it what type of equation we want, and if we want a linear equation, we would use mx plus b. Now we can type mx1 because we want to relate the x1 data to the y1 data, and then plus b. Now there's nothing really particular here about using m, we could use a. And so if I change a just represents the slope of this line. Now what we're noticing here is that very few of the data values, if any, go through that line. But specifically, if we focus on the statistics and we focus on this r² value, the closer r² is to 1, the better the curve, or the line in this case, fits the data. So we might see that there's a bit more of a curvature to this. We might think a parabola could work, or maybe even a different shaped graph. So let's just consider a parabola graph. We would type ax1 squared plus bx1 plus c. And we see that the r² value does seem to be a bit better. but we realize that if we were to go back in time, that the parabola would have been curving upwards over here. And so we don't necessarily need to worry about what's happening to the left. But we wonder if maybe overall a parabola is the best shape of this, because this parabola turns around, whereas our data values might not. So I didn't ask for a parabola regression or quadratic regression here. I'm just going to turn that off. And instead we want to take a look at an exponential regression. So we're going to type y1 tilde a times b to the x1 and then plus c. Now we know that the c represents a horizontal asymptote, and there's nothing to prevent the horizontal asymptote from translating from the x-axis, so I'm just going to say c is equal to 1. When we do this, in fact, let's take out that quadratic regression altogether. That was just to show you that there's lots of different possibilities that we can type in to come up with a curve of best fit. We're going to compare the linear and the exponential, both which require the solving for two parameters, in these cases a and b. And we see the r-squared value for the linear is 0.8668, whereas for the exponential growth we have 0.9898. So the exponential curve is fitting the data much better than the linear. So we're going to turn off the linear and focus on the exponential. Now we can zoom out a little bit, and when we zoom out we see that the trend over time would be for the population to continue increasing without bound. In other words, as x approaches infinity, y would approach infinity. This is not really realistic, and it's for this reason that the logistic function is a great option. The logistic function is going to allow the function or the graph to level off, in a sense to flatten the curve. And so we're going to type a over 1 plus b times e raised to the negative rx1. And so we get this regression equation here, and we see that we have the r-squared value is 0.9986, which is about the same, I have to admit, as the green exponential curve. But the benefit here, so all that's really saying is that for the data we have so far, that both the exponential and the logistic fit fairly well. But if we zoom out again, we see that it's more realistic that a population would level off rather than continue exponentially. So we really want to consider the real-world scenario before we pick an equation to model our data. So with that in mind, we have a logistic equation. We have the values for a, b, and r. I'd just like to point out that I can come up with a logistic equation using a slightly different equation. So instead of using the e to the negative rx, we could rewrite this as a over, let me put the a in there, 1 plus c times b raised to the x. And of course it's x1 again. And it's actually coming up with the exact same graph. If I turn off the exponential, then if I turn off the purple version of the logistic, and I turn it back on and I turn off the black version of the logistic, those are both the same equations. All we're really doing is rewriting the b times something. In fact, I could call this b here, so it's the same letter, and then I can call that c. So really we're saying that e to the negative r is the same as c. And I personally find the black version a bit tidier and easier to follow, but this is typically done because of reasons that we will see more in calculus. So either way, you can use both of these equations. But for the purposes of our course and assessment, we don't need to do anything in terms of finding the equation ourselves, and we just want to interpret what's happening here. So if we go back to looking at the question, we've created the scatter plot, we've performed the regressions, and we see that the exponential and the logistic both fit fairly well. However, the logistic is a bit more realistic when we take a look at the data as time goes on. And so we would use the logistic to model the population. Now, let's use that model to estimate the population of Florida in 2030. This question C is really a version of solve for somebody given something. And we're given the year 2030, which means that x is equal to 130. And so we're solving for y given that x is equal to 130. So we can go back into that curve and we can look at an intersection. Let's say this might be an easy way to do it, of x equal to 130. And if we click on that, we can get that the population is 23.716. But of course that means millions of people. So Florida's population is estimated to be what did we say, 23.6? 23.7. And don't forget the million, or millions of people, or just simply 23.7 million people. And then the last part is asking, what is the equation of the right-end horizontal asymptote of the logistic model, and what does it represent to the problem? Well, the right-end horizontal asymptote, right end and horizontal asymptote combined are saying that x is approaching infinity. And so as x approaches infinity, we want to know, what does y approach? In other words, what would be kind of the sustainable value of the population? What's the flattening out population for this particular model? And so we see that we have some line that seems to be somewhere between 20 and 40, and coming from these parameters, there's a number that is between 20 and 40. Let's just type y equal to the number that is between 20 and 40, namely this 28.021, and we see that that is the horizontal asymptote of this logistic curve. So what we're finding is that as time goes on, we wouldn't expect from the logistic equation that the population exceeds about 28 million people. So it does seem that our sustainable population based on this model is about 28 million people. So now we've seen the 4 different variations of using exponential functions within modeling. 2 are the classic exponential growth and decay models, and then the other 2 models involve an exponential term, but they're not the classic exponential growth or decay shape. The last type of modeling that we will look at is the inverse of exponential modeling, in other words, logarithmic modeling. The question really begs to be asked, why do we need logarithms? What do they do for us? Well, keep in mind that the input of an exponential function is an exponent and the output is a power. But for a logarithmic model, it's the other way around. The input of a log function is a power, so x represents power, whereas the output, y, represents the exponent. And so we're really focusing on the different sizes of these numbers. We know that exponents are countable numbers very often, 1, 2, 3, 4, 5, maybe -1 fractions, and so on. They can be big, but not nearly as big or as small as powers can be. So powers are very small or very large numbers, and exponents are more human-sized values. So we want to take a look at the very large and the very small. One place we will look at that is astronomical and atomic-sized data. So in number 9, we have that the diameter of an atom is about 1/10 millionth of a millimeter, and the diameter of the sun is about 1 million kilometers. Then we're asked a question, approximately how many times more than the diameter of the atom is the diameter of the sun? And so when we're looking at solving or answering this question, we need to come up with an equation and some variables. So we're looking for how many times more. So we're looking for how many times. How many times is some scale factor or multiplier number, and I might let that be called n for a number of times. And then we are talking about the diameter of the atom and the diameter of the sun. So I'm going to call this A and this S. And I have an equation here. How many times means to multiply. The diameter of the atom is the diameter of the sun. So I have an equation that says n times A is equal to S, and my goal is to solve for n. So I want the sun's diameter divided by the atom's diameter. And I know that this is going to be a number more than 1 because I want a bigger number. I want to scale the small thing. And scale just means multiply. So I want to scale this small thing by some number of times to get the big thing. In other words, when I divide bigger divided by smaller, I will get more than 1. So this seems pretty straightforward in terms of a problem-solving point of view. I just now need the diameters of these 2 quantities in the same units. So I'm going to let A, the diameter of the atom, be, well, I'll just write it out because we're given this value. We know this, and we're solving for that. So the diameter of the atom is 1/10 millionth of a millimeter, and it takes a lot of ink to write this number out, so maybe we'll have a simpler way to write this. We know that a 1 followed with 7 zeros is 10 to the 7, and then 1 over makes that 10 to the -7. So I have 10 to the -7 millimeters, or in scientific notation, 1 times 10 to the -7. And then I want to convert, I'll write that back again, I want to convert millimeters into meters because the diameter of the sun is given in kilometers, so I'm going to come up with a consistent unit. And so I know that between meters and millimeters that the meter is bigger, and so 1 meter is equal to 1,000 millimeters. And so I'm going to multiply to get rid of millimeters and introduce meters. And I know that 1 meter is equal to 1,000 or 10 cubed millimeters. And so the value of the green fraction, because the numerator and the denominator are equal, that's just equal to 1, not even equal to 1 meter, because the whole thing with the units will simplify and give us 1. So we end up getting that the diameter of the atom is 10 to the negative 7 meters. Okay, so we'll write that again, and then perform the same analysis, 10 to the negative 10 meters. And then we're going to do the same thing for the sun. The diameter of the sun is about 1 million kilometers. 1 million is 1 followed with 6 zeros, so that's 10 to the 6 times kilometers. And now we're going to multiply by 1 in a form that converts kilometers into meters. In this case, we know that kilometers is the bigger unit, so one of those is going to be more meters. And that's about 1,000, well, it's exactly 1,000 meters by definition. And since I have kilometers here in the numerator, I want to multiply fractions to reduce those. So I put meters over kilometers, and I put 10 to the 3 meters for every 1 kilometer. The value of the red fraction is equal to 1, and we end up getting that the diameter of the sun is 10 to the 9 meters. So when we input these two values over here to solve for n, we can get that n is equal to 10 to the 9 meters divided by 10 to the negative 10 meters, which leaves us with no units, and we just get 10 to the 19. So we would multiply by a very large number, 19 copies of 10, to go from the small atom diameter to the large sun diameter. And so what we're really talking about when we say what's the human-sized value here, we're just picking off the exponent. Rather than looking at the whole power, the logarithm is focusing on just the exponent. And so that's this term of how many orders of magnitude is this. When we talk about orders of magnitude, we're really talking about a human-sized scale. 10 to the 19 is so big, but 19 is human-sized. And so the number of times more that the diameter of the atom is, to multiply the diameter of the atom to get the sun is 10 to the 19. But the number of orders of magnitude is 19. So we're going to take a look at two other examples. One is a scale system, a logarithmic scale, which picks off the exponent for very, very large numbers. And the other is a logarithmic scale that picks off the exponent for very, very small numbers. The very, very large number scale is the Richter scale, which measures the intensity of an earthquake. The intensity of an earthquake is very large, and the Richter scale is the exponent that we would put on 10, more or less, to get that very, very large intensity power. So the Richter scale number is the exponent. There's more to the equation and more to the model for Richter scale than just this, and for the intensity of an earthquake, but we're just going to keep this quite simple. The base is 10, and I'm going to rewrite this as 10 to the exponent r equals the intensity I. It's not exactly the equation, but it will do for understanding how Richter scale comparisons work. So in number 10, we want to know how many times more intense, which means that we want to divide one intensity by another intensity. And because we want more intense, we want to put the more intense intensity, the bigger intensity in the top of the fraction and the smaller in the bottom. So we're going to come up with a number of times, which is going to be a big intensity over a small intensity. And in this case, the big intensity comes from the Indian earthquake compared to the Greek earthquake. So the intensity of India versus the intensity of Greece. And so the intensity of the India earthquake, well, we don't have the intensity, we have the human-sized understanding of that intensity. We have the Richter scale value. And so that's going to be 10 to the 7.9 for the big intensity. And we're going to divide by 10 to the Richter scale value, 5.9 for the small intensity. Now we can use our exponent laws, keep the similar base, and subtract the exponents. So the Indian earthquake at 7.9 on the Richter scale is 100 times more intense than the smaller Greece Greek earthquake at 5.9 in the Richter scale. That would be 2 orders of magnitude difference, but 100 times more. So you would multiply the intensities by the small intensity by 100 to get the large. The last example is to show you the opposite scenario. Instead of really, really large or large numbers, we're going to look at really, really small numbers. When we talk about a concentration of an acid or a base, we have some water, and inside we have some hydrogen ions. And that's what gives the solution its acidity or basicity. The more hydrogen ions we have, the more acidic, and the fewer hydrogen ions we have, i.e. in the concentration, the more basic. And so just like we had the Richter scale was equal to log of the intensity, and we can convert that into 10 to the Richter scale human-sized scale number, equals the intensity, we have that the pH is another human-sized scale. It's equal to the negative log of the concentration. Now we often use this notation of square brackets H plus for concentration of hydrogen ions. But we can just say C for concentration if that's a bit too much notation for you. And so rather than pH equals negative log of that symbol, we can write pH equals negative log of concentration. Now typically we want to write things in our friendly form, so our exponential form would be negative pH equals log base 10 of C, and therefore 10 to the negative pH is equal to the concentration, and the concentration is measured in moles per liter. So if you only know one version of the equations, know the exponential versions, and then be able to rearrange from exponential back into logarithmic form. So in this first question, I'll just clone the page. We are asked to come up with the hydrogen ion concentration for each item. We've got sour vinegar and a pH, and baking soda with a pH. So first of all, we're going to come up with the concentration for vinegar. Now keep in mind, we just said that concentration is equal to 10 to the negative pH. So the pH is the exponent, and the concentration is the power. So the concentration of vinegar is going to be 10 to the negative pH, and the pH of sour vinegar is 2.4. And that would be something measured in moles per liter. And we can work that out to a decimal in just a minute. We'll do the same thing for the baking soda. So the concentration of the baking soda is going to equal 10 to the negative of its pH. Now, these are going to be really, really small numbers, and that's indicated by the fact that we have this negative here. This is the same as saying 1 over 10 to the 2.4, or 1 over 10 to the 8.4. So the fact that we're dealing with really, really small numbers here is indicated by the fact that we have a negative in the exponent compared to the previous question. So let's just approximate 10 to the negative 2.4 and 10 to the negative 8.4. And so this seems like a big number, but this is really exponential or scientific notation, so we have to make sure to write that really carefully. So the first one is going to be about 0.004. So we have 0.004, and that's moles per liter, and that is approximate. So is this approximate? And then the other one was 3.981, so 4 times 10 to the negative 9 moles per liter. And so this is written as a decimal as 0.123456789 moles per liter. So these are really, really, really small numbers, and this one is much smaller than that. So what's happening is we have a pH scale from 0 to 14, and 7 is neutral, and then all of the concentration of solutions that lie between a pH of 0 and 7, in other words, whose concentration has an exponent of negative something between 0 and 7, will be considered an acid, and then everything between 7 and 14 is considered a base. Okay, so we found the hydrogen ion concentrations for each, and now we want to know how many times greater, so the same question again, is the concentration of vinegar than that of baking soda. So again, we're setting up a fraction Let's clear the page. We're setting up a fraction for n, and we're taking the concentration of vinegar over the concentration of baking soda. So we have 0.004, which is 4 times 10 to the negative 3 moles per liter. And I didn't write down which one is which, so I'm going to circle vinegar in blue, and then baking soda in red. I will put that underneath. And so we see that the moles per liter will simplify, and we'll see that the 4's will divide because these are joined by multiplication, and then we just need to simplify the exponential part. So 10 to the negative 3 minus negative 9 gives us 10 to the 6. And so the number of times greater is 1,000,000 times greater. Therefore, vinegar is 1,000,000 times more concentrated than baking soda. Oops, let's write down the right words. More concentrated than baking soda. But then the number of order of magnitude is just the exponent. The logarithm would just pick out the exponent. And so this difference, well, let me write it differently. This is an order of magnitude difference of 6. So what we're really seeing is the difference between using the power and using the exponent to explain or to understand the kind of the size of the numbers. So we use logarithms when we're really focused on the exponent. And we're focused on the exponent when maybe the powers are really too small, like in concentration, or really too big, like with intensity of an earthquake. Similarly, the diameter of an atom is a really small number, and the diameter of the Earth or the Sun or some planet or astronomical body is really, really large. So hopefully that gives you an understanding how we can use the logarithm to bring more meaning to the size of the numbers we're working with. Well, that wraps up our exponential growth and decay plus the other variations of exponential and logarithmic modeling. Just to get more practice and more experience, do as many problems as you can and make sure that you're understanding from as many perspectives, numerically, graphically, algebraically, as well as verbally. That's all for now.